Hello and welcome to our first lecture for the course Introduction to Data Analytics. In this lecture and perhaps the next few lectures, I'm going to be providing you with a course overview and giving you a detailed description of what we will be covering during this course. Let's start off with a little bit of logistics associated with the course. First thing is there is a good amount of information available on the course website. So I just wanted to make sure that everybody can avail of the course outline, the syllabus, the reference books and so on. It's all uploaded on the NPTEL website and you should access it so you have the appropriate information. The second thing is that the forums in the course are a great resource for answering many of the questions that you might have or that you might come across during the course. Most of the cases, the professors, myself and Professor Ravindran, we will try to answer some of your questions. At times we will have teaching assistants help us with answering questions. And most importantly, many of these questions can be answered by your own peers. So I really encourage you to use that resource and also contribute to it in any way that you deem fit. If, for instance, we feel like a particular question has not been answered appropriately or it keeps coming up, we will definitely join in and get in on the discussion. So definitely try to use that as a resource. Before I started, there are already a lot of questions on the forum, so I just wanted to address one or two of them. They pertain to the course at large. So the first question relates to the course style. For instance, is this course going to be very theoretical? Is it going to be very case study based? So on and so forth. So to give you a feel for what this course is going to cover, the course is not going to be only theory or highly theoretical. We're not going to emphasize extensively on the pure math of the course. There might be some amount of math and some amount of programming, but we're not going to go in depth in derivations and so on. The course is going to be heavily conceptual, and it's going to try and have as many applications as possible. So we are going to give you the whats and whys of data analytics, ranging from the statistics to the machine learning. What techniques and tools will you apply where? Why do some methods work in certain situations and not others? How do these algorithms work? What is the background logic behind it? And we're going to give you lots of applications. We will be assisting you with a little bit of how. So how do you implement this algorithm, or what kind of software could you potentially use and so on. But the course itself is not going to be a tutorial styled course. So it's not anything that you can essentially get from the help file of a package that you're using for data analytics. We're not going to be repeating that here, so that we believe that we're adding more value by spending our time and giving you really the core concept. Syntax you can learn from one software to the next. Which brings me to the next core area, which is the software and programming area. Many of you have expressed concern or have questions about what software we would be using, what programming languages, how much do I need to know. So the main languages that we're going to be using in this course are R and MATLAB, and occasionally we will show you how it can also be applied in Microsoft Excel. But again, it's not going to be tutorial style. We won't teach you the nuts and bolts of how to use R, and the code itself that we would be expecting or teaching would be fairly basic and more like command line instructions. So it would be fairly easy to pick up even if you did not know the software per se, but you had some comfort level with basic programming. So with that, I've covered some forum questions and basic logistics. So let's dive into our course overview. So in our course overview, I just wanted to give you the basic module list. Now this is available on the course website, and the basic module list just gives you the topics that we are going to be covering in this course. So we will be having descriptive statistics and inferential statistics. That's the first two broad areas. Within descriptive statistics, we would also be covering some amount of probability and probability distributions. We then move on to more advanced concepts in inferential statistics, namely something called the ANOVA, or analysis of variance. We will be talking about what where and why we apply that. We will introduce regression, something that you might have heard of. And then we move on to what we see as the main focus of the course, which is machine learning. Both an introduction to it, core concepts, how do the tools and what are the tools and techniques that are there, how do they work. And within that, we would be talking about both two classes called supervised and unsupervised learning. And finally, we come to this module on what do we do when you don't have data? How do you go about what is data analytics when you don't already have the data? So there's a lot of interesting work there. So don't worry if at this stage you don't understand some of the words that I have used. So that's what this overview is for, to give you some idea of what it is that we're going to be covering. I'm now going to go step by step, talk about each of these modules, and place them and give you some idea of what is the core concept behind them. Now again, the purpose of this is not to replace the actual class. So in the actual class, for instance, I will be giving you far more thorough treatment, and so will Professor Ravindran. But this is really to help you get a first class view of what it is that you will learn at the end of this course. So great, let's start with our first module, which is Descriptive Statistics and Exploratory Data Analysis. Here we're really talking about how do you describe data. So we would be one of the main things that would be introduced here is data visualization techniques. So this primarily concerns different forms of graphs. How do you represent a single variable graphically? How do you represent relationships between two variables graphically? And typically we are dealing with a data set. So what kinds of graphs and what kinds of tables are best suited, especially also given that different variables are of different types, and for different variable types are there different ways of representing this data. So visualization is one part of the descriptive statistics, and we will spend a few short classes there. We then move on to summarizing data. So this is a part of descriptive statistics, which is okay. You have a data set. How do I summarize that data set? How do I present it to you in a single statistic or a set of statistics? Out here, for instance, we will be mostly concerned with something like measures of central tendency. What do we mean by that? You might have heard of the words mean, median, and mode. And even if you've not, I'm sure you've all colloquially used the word saying, you have this data set, but what's the average? So if it's a single variable especially, what's the average, or what's a typical value in that data set? What's a value in between? And these are all very colloquial ways of talking about it, but there are various different measures of central tendency, and different measures express different properties associated with the data set, and we will be going into that. Another area is also measures of dispersion. So you might have heard of the words variance or standard deviation, and essentially what that captures is an inherent variability. So we spoke about this concept of mean or measures of central tendency, but how does the data itself vary around that average? And that's what we will be talking about there. We'll focus on measures of dispersion and measures of central tendency. But beyond summarizing data through these measures, we can go even further. And probability distributions are the richest way of expressing a data. And they do so because you don't just stop with saying this is the mean, or this is the average, or this is the standard deviation. You almost literally express it as 20% of the data is below this value, 30% of the data is below this value, and so on. So when you do that, you not only get an idea of the dispersion and the centrality, but the entire characterization of the data set. So, we will be talking about probability distributions as well there. Okay. So, I think that gives you some sense of what descriptive statistics really seeks to accomplish, and that is what we will be covering in that module. We move on to the next part of the course, which is inferential statistics. The idea here is one of populations and samples, and I am going to explain to you what these words really mean. The idea here is that the data that you have is essentially some sample from a broader universe that is or that could be creating this data, and this broader universe is what we call the population, and the population can be like a finite very large data set, and you do not have that entire data set, which is why you need a sample from the data set. But it could also be something more conceptual. Essentially, this data does not physically exist anywhere, the population data does not physically exist, but it is the concept of this really large universe of potential data that you can get, but you essentially have only you can only get a sample of the data set. So, perhaps I mean just to give you a stronger intuition for it, let us just talk about one or two examples. If you took, for instance, the height of all IIT Madras students, let us say the height of all IIT Madras students. Here is a case where you actually have a finite population. You defined your state space, you have defined that space as the data is ultimately the height of all IIT Madras students as of today, let us say as of 2015. That is a very large number, and you might not have the data. So, you might choose to take a sample from the data. So, you might choose 20, 30 students and go actually measure their heights, and that is your sample. And here the population would have been the height of every single IIT Madras student as of 2015. I will give you another example where it might not be a finite population. So, you might say, well, I have this manufacturing process that makes a certain product, and I am interested in the dimension of the product. Now, let us say I go and change that manufacturing process, and I am interested in measuring. So, let us say it is the width of a particular piece of metal that comes out of this machine. Now, the population here would be essentially infinite in size. It could potentially be the width of infinite number of metal pieces that come out of this particular machine, and you're not interested in actually getting that entire population. You couldn't, but you could still have a sample. You might have just collected about 20 pieces of such metal, and you have a sample. Now, what's the point of all this? Why is this an important concept? This is a very important concept because in many instances we find that we are not satisfied with just describing or giving you statistics about the sample. You are far more interested in saying something about the population. So, for instance, I might be interested in saying something like the average height of IIT students is less than 130 centimeters or some such number, or 150 centimeters. The average height of IIT students is less than 150 centimeters. Here, note that you are making a statement about the population. You are making a statement about the average height of IIT students, and we said the height of IIT students is the entire population. But you have taken only a sample of 20, 30 students. You do not have data associated with the population. So, is there something you can do with this statistic? That is, you can do with the sample of 30 or 40 and say something about the population. Another example instead could be something like, let us say I have I'm a toothpaste company, and my job is to put certain amount of fluoride in the toothpaste, and let us say I am interested in putting about 1000 parts per million of fluoride in my toothpaste tubes. Will every single toothpaste tube have exactly 1000? Probably not. And what is my population here? It is potentially every single toothpaste tube that I have sent out to the market, right, or I could be sending out to the market. But I can do one thing. I can go take a sample of about 10 or 20 tubes or 30 tubes, measure the amount of fluoride in that, and see if the average amount of fluoride in my toothpaste tubes is equal to 1000 or less than 1000 or greater than 1000. This is with the full recognition that not every single tube is going to have that exact amount, because the world is not a perfect place, the world is a noisy place. But is my average equal to the value I think it is, or is my average less than or greater than the value I think it is? So, the whole idea, again, just to kind of recap what inferential statistics tries to capture, is that you now have split the world into a population and a sample. A population could be finite, or it need not even be finite, but it is essentially you can think of it as this very large universe of data, and all you are getting is a sample. All you can measure is from the sample. But is there something I can do with this sample to make a statement about the population? And those are the tools and techniques that we will be discussing there. And it goes beyond, for instance, the two examples that I gave. For instance, the two examples that I gave, we got a sample and we compared that to some number we had in our head, right? We said, is the average IIT student less than is the average IIT student's height less than 130 centimeters, or is the amount of fluoride equal to some number x? But you could also be comparing two samples and thereby essentially comparing their populations. Is the average amount of fluoride in toothpaste brand A equal to the average amount of fluoride in toothpaste brand B, and extend that even further, A versus B versus C, and so on. So, the core idea again is that you are not confined to one sample, you could go to many samples, and the idea of going to many samples is what gets captured in a technique called ANOVA, or analysis of variance. We are going to have a separate module on that as well. But again, stepping back, are we living in a world where we get samples of data, where there is a bigger phenomena, but can I use these samples to make statements about the broader phenomena? So, that is what we will be covering in the inferential statistics part of the course. We then move on to something that many of you might have heard or encountered, probably has been the motivation for you to even maybe take this course, and I am talking about regression. When I say the word regression here, I am going to actually start using the word regression analysis, because the word regression itself can be used to cover many highly related but slightly different concepts. But we are going to talk about regression analysis, and regression analysis is a great segue, it is a great step going after inferential statistics and going before machine learning, because regression analysis uses inferential statistics. You can't say regression analysis is only inferential statistics, it uses inferential statistics, but it also uses many other tools. It uses optimization, it uses some concepts from descriptive statistics and so on, and it has a lot of overlap with machine learning. A regression analysis per se might not, in many courses or depending on who you ask, might not come under necessarily the umbrella of machine learning, because regression analysis has been there, been around far before say machine learning has. But in a sense, it tries to tackle the same problem statement or a very similar problem statement that some of the more advanced techniques in machine learning try to do. So, it is a great thing to learn and understand right off the bat, and so we would be introducing a regression to you in this course. With the regression itself, we are going to start with the simplest form, simple linear regression, and we are going to use fairly simple techniques of doing it, called the ordinary least squares techniques. And right now, let me just give you again a very basic intro to what a regression is. Again, like I have mentioned before, this is not to replace the class that we will have on regression. All of these things that I am talking about today, we are going to go into it in great detail as we go through the course. The purpose out here is to let you know what you are getting into in the course at this stage. So, Let me just spend a few minutes and give you a very brief intro to what a regression analysis tries to do. The regression analysis is essentially about creating a relationship between the dependent variable, you can also think of that as the output variable, and one or more independent variables, and you can think of the independent variables as input variables. We are definitely going to talk about some examples here, but the core idea is to create this relationship, and one of the simplest ways of creating this relationship is to fit a line through the data. What do we mean by fit a line through the data? Take your simplest example. You have the independent variable, and maybe we are best suited with some examples here, but let us say your independent variable is the amount of rainfall that a particular region in India receives, particular rural region, and this is collected over the course of a year. So, it is the annual rainfall that a particular region in India collects, and the output variable is the amount of crop yield. So, amount of rice that grew, amount of wheat that grew that particular year. So, the core idea is the independent variable is the rainfall, the dependent variable or the output variable is the crop yield. Why? Because we might suspect that how much rainfall, depending on how much rainfall there is, that is going to influence the crop yield, that the crop yield, which is the output, depends on the amount of rainfall. Maybe we are right, maybe we are not, but what we are essentially doing is taking pairs of data from different years. So, year 1, how much did it rain, what was the crop yield, how much wheat or rice or crop did we get. Year 2, how much did it rain, how much crop. So, you have this data set, right, of inputs and outputs, independent variables and dependent variables. The core idea is, can I create a relationship between these two variables, and the simplest way is to fit a line through this data. And you can see in the slide in front of you that I have just created an example graph where the x axis is essentially the independent variable, how much did it rain, the y axis is how much, what was the crop yield, and the idea is if you can fit a line through this data, that line in some way represents that relationship between these two variables. You can think of many more examples like this. For instance, maybe your independent variable is exercise and your dependent variable could be something like weight loss. In this particular case, the line, however, will look very different. The more you exercise, the greater the weight loss, but if you thought of it as, if you thought of the loss, it depends on how you think of the loss, right. If your y axis, the dependent variable for instance was your overall weight and not the weight loss, then you would have a line that started from the top left corner and came down to the bottom right corner. But that is fine, that is still a regression in one way or the other. As long as you are trying to fit a line through the data, that is what you are trying to do. There are many more examples that even come from engineering. Some of the early experiments have been in trying to understand voltage as the independent variable and current as the dependent variable. The frequency to the inductive impedance was another one that has been tried like this. Another great example from mechanical engineering is essentially speed of the vehicle to the mileage that you get from the vehicle. So, at different speeds are you getting different mileages? Is there some relationship between these two variables, and how do I quantify that? But the examples can be endless, but the core idea with such an exercise typically tends to be one of two things or either both of them. One is to capture that functional relationship so you understand the system you are dealing with, right. And this requirement is prevalent, and it is not mutually exclusive from this other requirement, which is, given the independent variable, can I predict the dependent variable? So, the first one, the more obvious one is, I need to know, I need to understand my system. So, by doing this data analysis, I understand how rainfall affects crop yield, but there might be another goal. another not unrelated goal, but another goal, which is given some amount of rainfall, can I predict what my crop yield would be? Now, this has some critical advantages. This has many business applications, and to give you an example, keeping with the same example, now given the amount of rainfall there is, if I can predict what the crop yield would be, then as a government, can I institute certain policies for relief for farmers? Given the amount of rainfall there is, if I am, for instance, providing insurance for farmers, can I come up with a prediction of what their crop yield should have been? So at least I am not in the dark about what it should be. Now, with each of the other examples we spoke about, we can also think of cases where being able to predict what would happen or what the case would be for a given instance has a lot of advantages for us. And many of the machine learning techniques, for instance, that we are going to be focusing on really emphasize this prediction part. How accurately can I guess what is going to be? And some amount of it might be that it's really helpful to guess that dependent variable, the output variable, because it's not possible for me to always measure the dependent variable. I've measured it to you for some amount of time and given you some data so that you can go and build models based off of it, but it's not possible for me in real time continuously keep monitoring that variable. So prediction becomes an advantage there. Another advantage could be that the dependent variable actually takes place at some point of time, however small, after the independent variable takes place. An example that's often cited is ambient temperature and number of heat strokes in a hospital. So that if I just knew, if clearly these two variables could be related, that the dependent variable, which is the number of heat strokes appearing coming into a hospital, is some function of the temperature outside. If the temperature outside is really cool and the sun is not out, you are not going to get that many heat strokes. I mean, that's just reasonable, right? But now, because there might be a time lag between when temperatures peak and when people actually physically arrive at the hospital, can I be better prepared? I use some historic data between temperatures and heat strokes and fit my line and build this regression model. Tomorrow, I am just going to use this regression model and say, oh, the temperature is X. At a temperature X, can I use my regression line and predict how many heat strokes are going to arrive at my hospital, and therefore I will be better prepared at the hospital. Okay. So I hope this gives you some insight into what regression is and what it seeks to achieve. And with that, we conclude our first session of the course overview. In the next session, we will be continuing with giving you an overview of the course and introduce the more detailed sessions on machine learning and so on. So look forward to having you join us then. Thank you for participating today.